Test one, yeah. It's time. And I started wondering, these lights strategically placed where I, like to settle down, I have to envision you in your underwear and I can't see anyone. So that's throwing me off. You ready? All right. Yeah, all right. Memory. Okay, good. I got one. I know there's one person out there. I appreciate it. I'm going to talk about Java memory management and really garbage collection as a whole, and maybe even some details on ergonomics. This was this is a weird thing. This is the talk, or close to the talk, that kind of started my experience in speaking, so to speak, years ago. It's where I got my Java 1 Rockstar and that kind of thing. So I've been in the space for a while. I'm not an engineer on HotSpot or JRocket or any of that, nor do I work for Azul. What's that? Oh, you are? I could see one person and they got a hand raised. It's just I was involved with trying to debug and test some production level type stuff, and that becomes important and germane to our conversation. Now, I struggled with this a bit. I did intend, and still intend, to talk Java 10 and 11. What I struggled with is, it feels like to me, like there are things to know along the path to where we ended up that are helpful in the process of understanding where we're at. And I don't know how to break that out. So I'm gonna start there. I'm gonna start at theory, and I'm gonna get into some old parallel GC and talk about its pros and how it failed us, and then I'm going to talk about some CMS, and then I'm going to go right into G1. So, anybody who's been doing some Java in the 10 and 11 space, they're expecting to be on G1. That's the default. You could switch it out, though, and there's actually even more things we could talk about. We could talk about Z or Shenandoah or some other garbage collectors. That space is growing. Now, here's the thing, kind of the value prop that I feel like I'm coming with here is I'm expecting that this is mainly developers. But when are you most interested in this topic? I would submit that it is most likely you're interested in ops when you're in production. That's when that concern is when you need it. And I don't know about, in Europe, but in the US in general, there's still people on 8 in production. It's very, very common. In fact, the scuttlebutt recently with, you're going to pay us, we don't know if we're going to support, blah, that has caused some great concerns. So we'll see how that translates. But this is perfect timing, in my opinion. It's perfect timing to be talking about this and where we're going with this because it's necessary. We're going to start seeing this in production, this being Java 10 and 11. Frankly, I do expect people to take, most organizations, I'm expecting to take a big jump. They're probably going to jump to 11. And it has more likely to do with the longevity of the different releases and that than it has to do with numbers. So, and Java 11 is expected to be a long supported distribution. So with that, let's get going. I guess I'll save some questions towards the end. I actually prefer more interaction, but we have a system for that. I will make sure to address questions. I work in the Java space. I worked in Java since '97, so pretty early on. I'm actually, as of up until maybe a month ago, I was mainly writing Scala code. So, and I dabble into Scala, Groovy, do a lot of Groovy testing. It doesn't matter. It's all Java ecosystem stuff, right? Okay, so again, focuses on production. If you're concerned with production, oftentimes it's because you've reached a moment that you can't sustain, and we need to talk about what that means. In all likelihood, you're running in a virtualized platform. You may be running in a cloud, and the first thing that you should probably do is analyze everything but the JRE as your culprit. Caveats there, right? So with that said, there is a book that is dated. I was talking with Charlie a year ago, maybe 2 years ago. They said they're coming out with another version or edition of this book. That hasn't happened. I have changed my vocabulary to match exactly what comes out of this book. I still think it's a germane and useful book. It is not valuable to you if you're wanting to dive deep into G1, though. It has nothing on it, actually, to be transparent about it. And I'll make sure to surface those vocabulary changes as they come up. Probably the one that's most challenging for people is talking about throughput or promotions or tenuring. There's a lot of confusion around tenuring. We'll get into that in a second, all right? So somewhat of our agenda. I'll start out by saying, hey, there's lots of things. When your JVM spins up, and now it's running Java bytecode, right? There's lots of things going on. The first thing that it does is it tries to check out its world. It goes, what world do I have? Now, assuming no flags, it can go off of what it can detect, and there's magic that happens at that point. I'm sure you've seen it. If you launch on a unicore, I jokingly refer to it as, it's one processor, right? Well, magically, you are in client mode, and there's lots of things that means. It's important to understand that. Why? Well, I could spin up a Docker instance, let's say. I'm living in a container, and I have assigned it to one core. Now you have to get into a little bit of C groups to understand what's happening. If you rely on CPU sets versus CPU shares, it matters. Fortunately, almost all of us use CPU shares. This has a different consequence to it. If you had CPU sets, now that might be advanced for those who are less familiar with C groups, but all it means is, from the JVM standpoint, I can only see one core even though I'm landed on a 64-core box. It starts in client mode. All of a sudden, all my compartments and expectations are changed. The world is different. We'll talk a little bit more about that in a second, okay? But it's actually, you could consider it to be worse the other way around. I assigned you to have one core of time, essentially, and I land on a 64-core box. The ergonomics at startup say, you know what? If I have 64 cores, here's the funny part about the JVM. Forever, actually. It always thinks it owns the box. It acts as though it owns the box. That has always been true, right? So if you put other things on it, it's in contention with the resources that it expects. If it spins up on a 64-core box, it expects that I can utilize all these things, which means that I will spin up, by default, I will seed, essentially, the fork join pool with 64 threads. And I will have the number of garbage collection threads of 64, which could have some significant impacts of inefficiencies. Now, it depends on how efficient you need to be, right? Like, it generally works great. You're usually abstracted from those details, and you don't care. But as we start to move into analytics, which in most of the clusters that I've been in ends up having 64 cores, you might be impacted by these things. You might be experiencing things you hadn't prior, is my point. You've never run on a 64-core box. You never experienced what that's like. Great. That's awesome. But when you do, you might need to be aware of those things. So there's these little things about ergonomics that are important to address it first. So is it an operating system issue? Did you over-provision the VMs, meaning I'm spinning in and out of disks to make room for VMs? Those are the first things that I would be doing if I am dealing with a production issue. Now, with that said, I'm going to wave my hands away and mainly talk JVM stuff. Let's assume now we have an issue and that it's JVM-based. There are some accesses we have to worry about. They're the things that we're almost always tuning for. The first is footprint. Now, if you're working in a data center, awesome. Most ops people working with JVM, they just think they have as much as they want. It so happens about 6 years ago, I wrote the in-flight entertainment system for Singapore Airlines for GoGo entertainment system. It was their first autonomous system, and I had a constraint, 512 megs. That's all I'll ever get. Now, I had a really also good constraint, which is I only have to serve the people on the plane. Right? It's 400 devices or 400 seats, right? So. But that was a real constraint. There are things I could not do that challenged the other accesses because I was limited. If that is not your constraint, well, then you're usually tuning for latency or throughput. And we'll talk, as we get towards the end, the value that G1 provides in trying to get to that space. You're doing Java. Why are we even here? Why do we even have to talk about this? How great. We're running Java. You never have to worry about memory, right? You don't have to worry about it at all. Yeah, until you do. So, and I don't want to convince everybody, if you're at a certain level of scale that allows you to ignore it, that's great, really, and I mean that. At higher orders of scale or larger, and it depends on the application. Let me pause for a second. I tend to focus on microservice-based architectures. What does that look like? It looks like a JVM that is handling RESTful calls usually, HTTP calls. They come in, they go out, and it handles thousands, hundreds, millions of them, right? That's the world. So it acts on something very quickly, and it responds to a request very quickly, and it achieved its goal. That is strongly different than if I am building out like a Spark or an analytics-based architecture. If I'm in Hadoop, if I'm in Spark, that model tends to have extremely large VMs, in which case the response time isn't the primary axis that you're concerned about. Speed matters, which is why people are moving from Hadoop to Spark, but does not matter as much as having all the information that I can then build a model around. So having a large model in memory becomes more important and adds value. You see the difference? That would be true if I was talking client-based as well. So I address that now because I will commonly speak to microservice-based architectures, and you might be thinking, hey, that doesn't work for this, or hey, what about that? Challenge me. Ask me questions. I'm happy to go into the other architectures or talk about what you might do differently in that space, okay? And I don't know why that's my preference to talk about. That's just the model. Maybe it's just what I've been working on mostly. Okay, so let's talk about how garbage collection works. First of all, it's a necessary evil. It's something that has to happen, but it takes away from what we really want. What we really want as a developer is to execute some kind of business logic. We love the fact that we're abstracted from this thing, and we'd love to not talk about it, frankly. So you being here is odd, right? Like, we shouldn't have to be here. But we are here. There's this magic that happens. All VMs make an attempt to reduce the amount of time that you will do that. And there's a technique that we use to do that. And what it really means is we put objects, we classify objects generationally. And we say that if and you got to be careful again. When we think of generations, we often think of ages of things, like how long. In other words, we measure it in time. We do not measure time for ages of objects in the VM. What we do is it's like living in California and you survived an earthquake. You're now 1, right? And if you survive another earthquake, you're now 2. So if you survive a garbage collection, that is your age, essentially, right? I'm trying to have a little humor with it. Hopefully that works okay. But so that's the aging of things. And you know what? If we had elderly objects that have just really, they've been around for so often, it seems like they will never go away. We should move them away somewhere. We should put them in the elderly home where we'll visit like Easter and Christmas. So you'll see them less often. Why? Because if I have to come and visit every time, it takes time away. I would rather visit something or check on something that hasn't been around that long to see if it's going to die, because it likely will. And this is the truth of it. Now, here's the hard part. The hard part is that if you've been in Java for a very long time, or you've been trained by someone who was in Java for a very long time, they have taught you things that are a disservice to you today, and has been for years, actually. But for some reason, it sticks within our ecosystem. I don't quite understand it. It used to be that things were terribly slow. Java 1, terribly slow for lots of things, in particular around XML, parsing, transformations, things like that. And that carried on into Java 1.2, 1.3, maybe even 1.4. All right, it was slow. So we would start to cache things. We'd create singletons. We were told never to create global objects, but we're going to do it, right? And that type of technique adds extra burden on the garbage collector today that I want to just make you aware of. If I had a goal, that would be it. Is like, as a developer, what can you do different? What you can do different is not act or do things in a way that would be against your benefit that the garbage collector is doing on your behalf. And in fact, I'm a little ahead of myself, but the garbage collector, the term, is a little bit of a misnomer. It's not correct. It's actually a garbage avoider. It avoids garbage. The garbage collector actually moves the living. So the more things that are still alive, it has to take care of and do stuff with. If it's garbage, it's lightning fast. So the more things that you create that go away in relatively quick amount of, now I'm going to say time, but it's really a reference to object. It's a profile of how much objects you're creating within a certain unit of time, and time really relative to the size of the space that you're in, which we'll need to talk about. If there's more garbage in there, it makes life just so much better. All right. So let's talk about it for a second. Garbage collection. First of all, we have this detection thing. Right? It's like, bring out your dead. Bring out your dead. Right? And that's, I'm not dead yet, so we move that person to another space. But we mark these things. Now, I'm talking theory a little bit at this point, but all VMs, I'm talking the CLR in the .NET space, the JVM, they all have an element of tracking these objects. The JVM has changed over time. And we'll talk about, at the core of it is root sets. If you want to dive into getting true understanding of how things are managed, it's at the root sets, right? But we have this need to be able to understand whether an object is referenceable or not, or whether it can be collected. That's the core of that. If you think about object creation in the microservices-based architecture, here's an easy example for you. What if I was to create a Spring controller, an MVC controller? I create an instance of this controller. How long do you expect it to live? First of all, how many are there of a type? So I've extended a controller. I've created one instance. Well, I gave you the answer. One. There's one instance of that thing. There's a singleton for a type of controller. How long do we expect it to live? Forever. That's right. Until the VM goes down. Now, yeah, you could, WebSphere, you could shut something down, bring it back up, whatever. We don't tend to do that. It's forever until the VM goes down. So there's one thing that lives forever. Of course, we're going to have more than one controller. But relative to that one controller, if we're heavily using it, doing request-centric invocations against that controller, how many HTTP request objects are being created? It's a challenging question because it's relative to scale and what you can handle. Assuming it's super successful and doing amazing things and has lots of clients, we could say thousands a second. How long does it live? Duration of the request. Response goes away. It's no longer available. We don't need it anymore. We don't need to track it. Why would I track it? So, orders of magnitude. I have objects. We call it a morbidity rate, which is a kind of a dark space, right? The morbidity rate. The morbidity rate of an object is fairly predictable. When an object is created, it has a high likelihood of dying early. That's the expectation. The JVM is designed and expects that. If it doesn't, we'll have to keep tracking it, and we'll keep tracking it until we move it to a different space. And we'll track it different period, if you will, right? So, and in the space of high morbidity, they outnumber by a large amount the things that live longer. So that's kind of the theory on it. So we break up the space. Now we start to get closer to JVM stuff. We have this new space and old space. The new space is where new things get created. We break up the new space into 3 compartments, Eden and 2 survivor spaces. Frankly, this is old school, but it's useful because I can't talk about G1 without bringing it up, unfortunately. All objects are created in Eden. So I keep getting asked all the time, is it possible to create an object so big it doesn't fit in Eden? And I'm like, yeah, but it's evil. You're supposed to laugh at that one. All right. The whole goal is now look at this. This is so cool. We get into these arguments, and they're kind of silly, like, hey, the JVM, the JRE, the memory, it has to be contiguous memory. First of all, there's nothing in the spec that defines that. 0 things in the spec define that. It's up to the implementations. But the JRE that we tend to run on that we're familiar with came from Sun, is now Oracle. Now the JDK tends to be, that's true. But there is no reason why that has to be true. And in fact, as we move closer to G1, it makes it even more irrelevant, that constraint. But there's some value here, right? I got a pointer here. And and I can even tell you that in Java, I can instantiate an object faster than in C, which sounds crazy. But the number of clock cycles that it takes to instantiate a new object in C can be in the order of like 50 clock cycles. But I can do like 10 in Java. Why? Because I'm literally just moving a pointer. It's at 0, and I just have to go to the size of object. I just keep moving this pointer. Garbage is collected, potentially is, these objects that are being collected are created could quickly die. We don't know that yet. But it's super fast. Why do we have 2 survivor spaces? Somewhat arbitrary. Let's talk about what happens. There's this arbitrary point of Eden, where I'm going to call it full. It's arbitrary because it's somewhat dynamic. Whatever full is defined at a given moment in time, we have thing T equals new thing in our code, right? So we created an instance of a new thing. New is your magic operator that consumes thing out of the heap space, and that's what we're talking about is heap. So thing T equals new thing. A pointer is moved, and there's like that oh crap moment where it's like, well, that pointer goes past our endpoint. What do? Well, that invokes a minor GC. A minor garbage collection occurs. They're way fast. Why? Well, a couple of reasons. One, we're just dealing with the new space, which means Eden and one of the survivor spaces, because only one of those is active at a given point in time. The other one is dead space in that moment of time. At the time we have a minor GC that occurs, all the living objects from the Eden space are moved into the next survivor space. All the remaining living in the current survivor space are moved to the next survivor space. And then we consider the next survivor space to be the new current, and we start at 0 again. And I always get this question, are we really moving objects? Aren't we just moving points? Yeah, we're moving objects. The objects move, right? It's like in this model, right? In this model, they move. Look how awesome it is if what we have at the end of filling up Eden, if it's full garbage, there's nothing to do. Absolutely nothing to do. Do we zero out anything? No, we just write over the old. So we literally do less work if it's garbage, which becomes a really important aspect of G1, by the way. Okay, so we have everything that we saw before. That is MX. If you set up max heap or min heap, that is the things you're talking about. Then we had this thing called Perm Space. Wasn't going to get much into that. There was a point in time when we thought, you know what? There's stuff that will never change, ever. It's permanent. We should have a space for that. Why? Because we don't want to visit things, we don't want to manage things if we don't have to, which is why we compartmentalize in the first place. And guess what? We were wrong. We were just flat out wrong. We were sucking things into Perm Space. The first point of pressure was JSPs, where JSPs had to be brought in, converted into servlets, then converted into bytecode, and then read as bytecode into machine code. It put a lot of pressure on Perm. Next pressure, XML. And I could go into more. I won't have time. You can hit me up later or in questions if you want. So we had these issues. There's some algorithms. I already walked through what a minor GC is. It happens when I said new thing, when thing T equals new thing. I try to bump my pointer. It bumps up against whatever max is. Max could be theoretical. Not theoretical, but could be, how do you define it? It could be a virtual limit. That's really the best way of defining it. And then we have survivor space switching. Oh, this is when max tenuring age occurs. Now, words matter to me. The fact I took an object and I moved it in new space to survivor space, and I might be bouncing it between the survivor spaces, that is tenuring. You are tenuring an object. You're basically keeping it in a nursery, expecting that it still might die, right? You're like, hey, if it dies here, I don't have to deal with it in old space, right? That's the expectation. That is the word tenuring, that's what it is. It is the movement of an object in the survivor spaces with the expectation that I will not promote it. A promotion is moving from the new space into the old space. That is very distinctly different. It's the same concept, right? But it's a distinctly different way of thinking when you're managing objects at that engineering level. So there is also a max tenuring age. By default, it's 15. If you jump it back, forth, over and over again between the survivor spaces, we're like, he's just going to keep on living. We might as well move him to the old space, right? So we do. And in fact, while I'm looking at a JVM under nominal conditions, and I see the max tenuring age is something like 1, there's a problem. That's the thing I'm probably tuning for. So there's little rules of thumb that I will throw out there. How does max GC work? Well, here's what happens. Thing T equals new thing. I bump in Eden. I'm like, oh crap, don't have space. I do a minor GC. I move a bunch of objects. And I'm tenuring over to the survivor space. Out of that activity, one of two things happened that resulted in the same thing. Objects were promoted. Two things that could cause it. I pass the max tenuring age, or I don't fit. I got to keep track of these objects, but they don't fit in the server space. So they get promoted into the old. I promoted an old. I have another pointer I'm managing over there. It stretches out, and it hits max. Oh, crap. Again? Yes. Now I have to do a major GC, which should also inform you that a major GC always is preceded by a minor GC. That's how that works, okay? And if you ever had those moments where you're like running along happily in JVM and things go really slow, that's your full GC. You've just experienced it, right? It's a really slow pause experience. And we can talk about predictabilities. There's a nice graph that goes through that. I can see I'm going to run out of time, so I'm going to speed along. So we introduced this idea. We knew, I say we, the HotSpot engineers, we all knew that Perm Space was broken. Things were bad. Between string pools and string management, between what is truly permanent. The fact that when the challenge is that when you look at MX, if you want more than MX, you have to bounce the server, right? Like that's a requirement. That has set the boundary for that process when it ran. But the same is true for Perm. When I have a Perm space, it's not native memory. It is memory that is being managed and allocated out of the JRE. And it has a default. The default depends, by the way, on are you in client mode or server mode, right? And it depends on which JDK you're on, actually, or JRE. That said, the normal default that I'm used to is 32 megs. And if you ever need, 64 megs, sorry, 64 megs. And if you ever needed more than that, well, you'd have to bounce the server. And that's just, you had to live with that. So we had these constraints that we wanted to fix, and we created something called metaspace. To a certain extent, it takes the same things that we expect to be semi-permanent, and moves them out, but it moves them out into a native space. And that was always the problem. How do I manage pointers that are pointing from native space into object space or heap space, and vice versa? And there is some management magic that needs to happen there. So we reverse it. Now, there's some challenges with that, in my opinion. For one, almost all the flags that we had for Perm space, like max perm size and that kind of thing, they switch out perm for meta, and there was a nice replacement. Except for you would probably never want to do that. So it's a little bit challenging, right? What I want to say here is that if I would have said my max perm space is 64 megs, and I just switched the flag to metaspace, and now I'm in the metaspace with that limit, I would realize, wait a minute, I probably don't want that. So let's just zero that out. Let's just be done with it. Now I have 0 for max beta means infinite, which means that if I had a class loader leak in a JRE before, it would be detected eventually. The VM would go down. If I have a class loader leak in the metaspace, now you got to be careful. This doesn't happen that often, right? It's one of those edge cases. But if it were to happen, you basically bring the entire node down. Or if you're in a container, you would pop the container's killer. So just be aware of that. A class loader leak at this level, because of metaspace and how it's managed in the native space, consumes into native space, it will affect the machine at that point. And metaspace is kind of an interesting thing, right? It's really a collection of metaspaces, which essentially is space for semi-permanent information per class loader with some overall global stuff on top of that. All right, so there's your different flags. The thing that's important there that will be new to you, if this is new in your space, is we didn't have expansion or free ratio before, and they're useful, right? What it means is, if I need to go get more native space, how much native should I get at a time? That would be the ratio. When should I get it? How much space should be left before I realize, oh crap, I might run out of this sometime, so I better fetch ahead of time? That would be your free ratio, right? So those are the different, or your space expansion. I might have those reversed, but those two flags are used for that purpose. They're very valuable if you have heavy use on your metaspace. All right, so now we know enough information on the GC stuff. I think I've captured most of these already, so I don't know if I need the slides. Please stop me if I'm going too fast. But the garbage avoider we talked about, retention rates, promotions, speeds of allocation. I think I said 50. I'm at 30 on a malloc allocation. All right, let's get to our different collectors. So very old school is the old parallel GC. And in large part, it is the thing I've already talked through. It works in the exact way I described old space and new space before. The thing about it is it has an incredibly fast and super predictable minor GC. I don't know if you could get better. It has to do with the fact that we don't have to track anything. I'm just going to take the living, move it over, tenure and promote, boom. There's nothing I have to track outside of that. There's no additional compartments to worry about. It's way fast. It also has very predictable full GCs. You can see up here that it's between 1 and 5 seconds per gig. So that's fairly predictable if you're looking for predictability, right? Now, as soon as we get to that point where it's taking too long, it's impacting my business. What tends to happen, or did happen, is people would start looking at CMS. Now, there's a group of people who claim CMS is the answer to all things, and you should always use CMS, and to which I call BS. The thing is with CMS is this. To me, it has a window. Before this window, I would use it at this point. Prior to that point, I would not use it. What does that look like? Prior to the need to CMS, the old parallel GC is just faster, especially for minor GCs. It's just faster. There's nothing to track. It's fast. At some point, I have some contentions, and then it becomes valuable because I can do concurrent. Now, I'm garbage collecting at the same time that I am allocating objects within my application. Now, as soon as you say that, I hope you've visualized the mental model that, wait a minute, I have one space, and you're saying something's going to come through here and just start putting objects in there, and another thing's going to go through here and start ripping objects out. And I hope you can visualize that, because it's strongly different than the last model we described. And it necessitates the need to keep track of things in a different way. It necessitates something we call the free lists. I need to know free regions for which I can allocate object space for. And it has a higher overhead. So here's when I would start to use it at this point in my scale, if you will. And then it gets to a point where all hell breaks loose, right? And it's tough to see when you get to this point, but here's the thing. It is always possible, given the right, give me the constraints and I will tell you how to do it. It's always possible to put a garbage collector in the stop the world model. You have object allocation or object creation that's outpacing your ability to garbage collect. You will always get to a point where I'm like, oh crap. And things are actually worse at that point. They're significantly worse because I have a bunch of things I'm tracking with my free list that I have to just okay, stop. Let's reset some stuff. And that takes significantly longer than the predictable old parallel GC. Everybody cool? So that's the different models. Let's move into G1 and see how things change a bit. Now, G1, first of all, what's G1 stand for? Anyone know? Garbage first. We've talked a lot about garbage today, right? Garbage first. Why would you put your garbage first? So what we're going to do, and this is the reason why I needed to talk about all the other compartments and kind of how they worked, is we're going to use all those compartments still. We're still going to have an Eden space. We're still going to have survivor spaces. We're still going to have old. We're still going to think in those terms. But we're going to take Eden and divide it by 2 megs across a number of memory locations and keep track of them that way. Now, if you had, I don't know, let's just pick a number. If I had 10 megs of space, and then I reduced it into 2 megs of space, what is is it higher, is it more likely or less likely that a 2 meg space would be full of garbage and have no living? Or is it more likely that I would have more garbage in 10 megs of space? Should be obvious, I hope, right? The more fine it is, the higher the likelihood that you won't find the thing you're looking for, like a live object. It's just the nature of statistics at that point. So if we subdivide these things, the goal being, if we have a high morbidity rate in particular, I have a 2 meg region, and I start allocating objects out of it. And then I need more objects than 2 megs, and I start allocating out of the next region. And I keep doing this. And at some point, I've filled all my regions of Eden space. Now, there's some algorithms underneath the covers that could grow out and have more regions of Eden if we needed it, just like the VM would grow naturally. If you didn't set MS to be MX, you have some growth space, and that would happen at the different region levels. If we filled all of Eden in this region set, the next question might be is, I've got this thing t equals new thing, and the question is, all my Edens are used. Is it possible that there is a region that exists for which it is full of garbage only? And if I can find that, I could just start writing. I don't have to move anything. I don't have to zero anything. I just start writing again. Do you see the optimization that's happening? What's the consequence? The consequence is I have more fragmentation. I have to manage, it's overhead. The extra overhead adds enough value that I can do things concurrently. And I will treat each region with the hope that in a world where I have a high morbidity rate in new space, that I will have a garbage region available all the time. If that doesn't happen, we'll have to go through some compaction, we call it. Or I may have to move some objects into survivor spaces. We still have tenuring ages to deal with. So this is the region space we're referring to. We're just going to slice and dice. Now you begin to see like this constraint we always argued about 10 years ago about how this has to be contiguous memory. It literally is ridiculous at this point, right? Whether it's contiguous or not is kind of irrelevant. Obviously, an implementation vendor is going to implement the way they implement. But we already are fragmenting. We're fragmenting everything for the benefit of doing things concurrently, with the consequence of having higher overhead, but seems to work because we can do it concurrently, right? That's the goal. As I said, it is still possible if you reduce the amount of memory, if you have a low morbidity rate, meaning you have objects living, and I have a high promotion rate, to outpace the G1. And that's the balance that you have to have. There's still a little bit of art. That's the thing I love about what we do. It's like this combination of like art and science, right? It's awesome. The science part, the part that is the hard work that we have to do, you're going to have to profile your application. What is your standard allocation rates? What are for a given use case? Now mirror that across your analytics. Understand the full scale of object creation across multiple invocations, if you will. And then understand adjustments of compartments to see how you might be able to maintain high throughput, which is the goal of G1. All right, I have some more on that. I've got a bunch of slides. You'll have them if you want. G1. So there's a number of things that are happening. Again, we've been driving a G1. We've even had it out for a JDK 9. You could have switched it into G1 collector. The goal is throughput with low latencies. The default, you can switch the default, but the default region sizes are 2 megs. Anything that goes over 2 megs is, I love the term, is referred to as a humongous object. It's humongous, right? So you can span across multiple regions if needed. That's all tracked for you. New object creations in these Eden spaces, as we described. We still are going to have a compaction that will go into a survivor space. Now that doesn't happen. Like if that thing was full of garbage, there's nothing to compact. So it would just be written over. So there's a little bit of intelligence underneath the covers that manage some of those details. Still go through the same process of having an old space to manage. It begins to pollute. That's actually the hard part. I feel like you have to go through the other history of how we were managing memory to understand why we even have an old space. Why does it have to have a special name? Why do we treat it differently? It's just another space I'm moving objects to. But that model still exists and is managed too, even in this change of G1. All right, so eventually you have a bunch of different regions scattered throughout your environment, and we'll go through this over and over again, all while the application is still running, meaning threads have, your application business logic was not starved, is the main point, by a thread that was never given up. Okay, this is the model that we went through. I talked through it to a certain extent. We have a young generation, we have a young collection. It's a little bit confusing. Here's why I say it's a little bit confusing. The term young generation is the same thing as the new generation, or the new space. And in the old days, the late 90s, we referred to it as young. At some point it changed to new, and now we're changing some of the terminology back to young again. So it can be confusing in that space, but don't let it confuse you. Still the same thing, new space, young generation. And we will go through these different stages of kind of the phase that the G1 is in. Hey, I'm just dealing with the young generation. I see another region that's garbage, I'm just gonna start writing over it again. At some point, I can't. At some point, I'm like, okay, I have more regions of Eden than I can handle, and I need to move objects out to a different, in other words, we're like, hey, I'm gonna visit those spaces less often. I don't wanna visit, it appears that this object's gonna live longer than I expected. So I'm gonna move it to a region I'm gonna visit less often, and that's gonna be that concurrent model right there. And then you're gonna have mixed collections that fall in, and we'll cycle between these phases. This I'm not gonna read, but I have found that people really like to have the information of what flags of control that I can have on my GC. Well, there's a huge list of things that we can modify and change. Oftentimes, and this is growing actually, we're still doing work on G1 to improve usually throughput or latency challenges. Oftentimes what you're encouraging to do is I'd like to stay underneath this amount of time. Also, what you also probably more likely is, hey, I have objects that are commonly humongous. I would like to have regions that are bigger than this. Now, you have a whole nother set of issues when you start going down that path, but those are the kind of things. Or you might want smaller. So, and this is kind of the thing we're playing with right now, if you want to call it that, is there are things we're still discovering. There's a lot more variables right now. We're trying to understand the impacts of those things. Most of what I've covered, as I mentioned, is microservice-based architectures. You start getting into Hadoop, everything goes to old, right? Everything lives for a very long time. If you're if you're using Eclipse or IntelliJ, it's Java on your desktop, everything goes to old. Essentially, it might as well. The longevity of something is strongly different. I have an old case study it might be worth just pointing out. It is super handy and useful to start looking at having a tool that gives you this information. Typically, someone very new to this space is just going to be logging out GCs out to logs. That's terrible. Yeah, we all start that way, and if you're really good, you might be able to glean from that what you need. That said, it's like stocks, right? You're like, hey, IBM's at 90. Do you want to buy some? You're like, maybe. I don't know. I need to know trends. I need to know trends. So there are graphing tools that allow us that access to that. Out of all of this choppy stuff that I was on a client site for years ago, and it was in production, I can go through more details if you want. Of all of this, the thing that's most concerning is that. That's the thing you're looking for. You're like, wait a minute, I had a full GC and I reclaimed a huge amount of old space, and that begs the question, why? Why is that true? Right? So there's a lot going on there. Most of it's irrelevant, and it's old. But the thing that you're concerned about is how come I was not managing my memory more appropriately? So we made some changes. Again, the details not terribly important, but you can see that essentially garbage collection or high morbidity rate in the new space with like this constant like 21 megs of old space because you just didn't need old. Now, the beautiful part about this is that if something hits us really hard, we get hammered. Then we're going to have something in old space that's going to absorb the hit, if you will, and eventually be collected, which is awesome. That's what its intention is for. That's a healthy thing. What you're looking for with regard to trying to tune things in this way is what's your nominal condition? What's normal, right? Or and you might target towards your high end. It depends on what your extremes of your normal versus high end is. But regardless, that's kind of what you're after. Again, I'll reference Charlie's book. I thought it was a good book. It's old. It doesn't have any of the G1 in it. So, dziękuję. I am going to see if there's questions. I was told there's this crafty. Oh, where is the? Oh, Java 10, Java 11. The Java 10, Java 11. This is on memory. So we're really talking GRE. There's no like Java uniqueness, and there won't be. Like there's some new elements in Java 10 and 11 where you have vars that you can define, and we have some string duplication management that we can handle. Everything that we talked about is stuff that you're going to have to deal with on 10 and 11. When we got to the point where we're talking G1, G1 is the default for 10 and 11, and hopefully that was accurate. If you feel like you were cheated, then let's come down and brawl it out right here in front of everybody. Raise hand and poll versions. Oh, somebody wants to know how. Well, I can't even see anybody, so I don't think polling in here is gonna help. Maybe we could go for cheers or something. Okay, people really want to know that. Okay. Project, lots of living objects, GC configuration. What is this question? Where you have lots of long living objects, GC should be, okay. So long living, it's actually, it took me a while to process, sorry about that. As soon as you have long living, like Hadoop-oriented situation, this extremism that we've been going towards G1, concurrent and then G1, is less helpful. I don't know if it's hurtful. Maybe the default works fine for you. I'm not saying that. I'm saying what you will end up with is large old space. And you should probably tune for that just right away, right out of the box. You don't need as soon as you know your profile of your JRE, you just own it. Because here's the problem. In a lot of organizations that are less mature, I'll just go that way, the only configuration they have on their JRE is MX or something along those lines. If you know the profile you're going after, you really should be you should definitely be affecting new space if you're microservice-based architecture. No question about it in my mind. If it's heavily used, request-centric, you definitely should be managing your new space in production. If you're on the other side, which was this question, if you have a lot of old, you should also probably be managing your new space. You know you're not going to gain value out of it. So that's a good question. GC times, that has changed over time. I still like Visual GC, and Visual VM comes with the JDK. With adding in JRocket, there's Flight Recorder. So Flight Recorder is probably what you want. That's a good question. Recommend for a good profiler. Profiling tools vary. It's a good question as well. I happen to be a real fan of MAT, M-A-T. It's an open source tool, which is great, based on Eclipse. That part really isn't significant. It is one of the better tools that will take you right to root sets and truly see why is this object being referenced still. If you're into thread analyzing, The threat analyzer toolkit is also really, really great. Beyond that, we'd have to talk and look at it. Things change a little bit when we start getting containers. You start to need to know a lot of extra stuff, right? Like what your C group constraints are, frankly, what your operating system scheduler levels are, whether it's fair share or not. So there's a lot of things that get grouped in together that you would need to be aware of in order to highly tune this environment. One of the problems that you get into is, again, you're running Kubernetes or Mesos ECS. All those containers in an orchestrated space land with CPU share. And what that, in the short, what that means is you land being allocated one core, maybe two core, but without changes at the operating system level, you could actually burst into more cores. You could burst into using all of them if all the other apps yielded their time. Now, the reason why that becomes important is because you could have something on the node you landed on that's bursting. It's not you, and it's starving you. Right? There's lots of things. So fair share becomes super important. Again, you got to combine the things we just talked about into the whole aspect of the picture to truly understand what's going on in production, especially in an orchestrated space. All right, I think I'm out of time. Thanks. Dziękuję.